All right, y'all, we're going to move on to section 5.2, and these are going to be called probability rules. So let's read a couple of these descriptions, and we'll go from there. So it says the sample space S of a chance process is the set of all possible outcomes. So when I'm flipping a coin, I could list my sample space S. There's only two possible outcomes, heads and tails. A probability model is a description of some chance process that consists of two parts, a sample space S and a probability for each outcome. So if I wanted to make a probability model for a flip of a coin, I could say something like this. I could say outcome, heads or tails, and then I could list the probabilities. Okay, the probability that I get a heads is 1/2. The probability I get a tails is 1/2. So that would be a probability model. Now what's important about probability models, okay, is the probabilities have to add up to 1. So 1/2 plus another 1/2 equals 1. An event is any collection of outcomes from some chance process. That is, an event is a subset of the sample space. Events are usually designated by capital letters like A, B, C, and so on. If A is the event we're talking about and we're interested in its probability, then we would write it with this notation. P of A means probability of event A. All right, so let's go through the first exercise here. It says create a sample space listing all possible outcomes of the sum of rolling two fair-sided dice at the same time. And then after that, create a probability model that illustrates the sample space of the sum of two dice and associated probabilities of those sums. Okay, so let's think about that. So when I roll one dice, I can get the outcomes 1, 2, 3, 4, 5, and 6. So those are the outcomes for the first die. All right, when I roll my second die, I can get the outcomes 1, 2, 3, 4, 5, 6 this way. All right, so what I'm going to put in this chart is I'm going to put the sums. I'm going to add these numbers up. And you'll see what I'm doing here in just a second. So in this chart, here's the first die, and die is the singular of dice, and this is the second die. All right, and in the middle, I'm going to put the sum. So if I get 1 on each die, the sum would be 2. All right, if I get a 1 and then a 2, that would be 3. The sum would be 3. So if I add these, I'm going to get a chart that looks like this. Okay. So in the middle there, in green, that's the sum. Now, that's not what the question is asking here. It's just asking for the sample space. What are all the possible outcomes? Well, if I look in this middle, in the green part, I see a number 2. 3 is a possibility, 4 is a possibility, 5 is a possibility, 6 is a possibility. All right. And 7 is a possibility, just looking at that first column. We have all those numbers starting at 3, but now it goes to 8. Okay, so I can get 8 when rolling 2 die. I can get 9, I can get 10, I can get 11, I can get 12, but I can't ever get a number bigger than 12. Okay, so right there, that's the sample space. All right, where S is the sum of rolling 2 dice sample space. So those are all the outcomes. Okay. And then the second part asks me to create a probability model. Okay. So in a probability model, we have outcomes, and then we have the probability of those outcomes or those events. All right. So the outcomes in your probability model, you have to put everything that's in the sample space. So the possible outcomes when rolling 2 die, the sum would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, how are we going to find the probabilities? Well, we're going to look inside here. There's 36 different outcomes in this green sum in the middle of this chart. Okay, there's only one of them that's a 2. So the chance that I would roll a 2 is 1/36. Okay. That's this one right here. I knocked out that 2. I took care of it. Okay. What about 3s? Well, there's 2 outcomes that are listed as 3. So that's 2 out of 36. And actually the numbers exist on diagonals here. The chances that I'm going to get a 4, well, there's 3 outcomes that are 4. So that's 3 out of 36. All right, 5, 1, 2, 3, 4. There's 4 5s, so 4 out of 36. The chances that I get a 6, 1, 2, 3, 4, 5 out of 36. Chances that I get a 7, well, there's 1, 2, 3, 4, 5, 6 7s, so 6 out of 36. If we go to 8s, there's 1, 2, 3, 4, 5 8s, so 5 out of 36. 9, 1, 2, 3, 4 9s, so 4 out of 36. 10s, there's 3 10s, so the probability that I get a 10 sum is 3 out of 36. There's 2 11s, so 2 out of 36. And there's only 1 12, so 1 out of 36. If you were to add up all these fractions, the sum should equal 1. Okay, the sum should equal 1. So this is our probability model. This is the this is the theoretical probabilities that you roll any of these sums. Okay, there's actually a game, a casino game called Craps that's all about rolling a set of 2 die. All right. So let's look at the rules now. The basic rules of probability. It says the probability of any event is between 0 and 1. So look at all of these outcomes or events. If you notice, all of these fractions are never smaller than 0, and they're never more than 1. Okay? The probabilities of all outcomes when added together must sum to 1. If I added all of these fractions together, it has to equal 1. Or if you did it as percents, it would have to equal 100%. Now, the third bullet says if all of the outcomes in the sample space are equally likely, the probability that event A occurs can be found by using the formula. And the probability of A would equal the number of outcomes corresponding to event A and the total number of outcomes in the sample space. Okay, so what does that mean? Like, let's say you just rolled 1 die. Okay. If you roll 1 die, you only get the numbers 1, 2, 3, 4, 5, and 6. Now, each of these are equally likely. Okay, when you roll 1 die, you have as much chance of getting a 1 as you do a 2. All right. Therefore, in that type of model, the probabilities would be 1/6. All right. So what's the probability that I roll a 1? Well, there's only one outcome with that, so we can simply do 1. And how many outcomes are in the sample space? 1, 2, 3, 4, 5, 6. Okay, so you can use a shorter formula. If each of if each outcome is equally likely. Okay. All right, let's read the next part. It says the probability that an event does not occur is 1 minus the probability that the event does occur. So going back to this example right here, the probability of not rolling a 1 equals 1 minus the probability of rolling a 1. All right. Because we know the probability I'm going to get a 1 is 1/6, well, the probability that I don't get a 1 would be all this stuff over here. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. So it's like 1 minus a sixth, which is 5/6. All right. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. Okay. And we'll get into that a little bit more. Now, let's talk about this term called mutually exclusive. Mutually exclusive, in some books they call those disjoint events, if they have no outcomes in common. So the best way to think about mutually exclusive is with a Venn diagram. If event A is this circle, and event B is this circle, and if there's no overlap, okay, then they're mutually exclusive or disjoint. All right. If there's no overlap in the circles in the Venn diagram, two events are mutually exclusive. All right. So like when rolling a die, if you make event A equal the odd numbers on a die, and event B be the even numbers, okay, event A would have the numbers 1, 3, 5 in it, and event B would be 2, 4, 6. There's no overlap. There's no number that's both in A and B. So these two events would be considered mutually exclusive. The outcome of one die. Right. On to the next page. Some notation. We already talked about this. The probability of any event is between 0 and 1. The probability of the entire sample space equals 1. So, what they're saying, based on this previous thing, here was my sample space for the sum of rolling two die. If you were to add all the probabilities of getting these numbers, like down here, it equals 1. Okay, that's what that part means. All right, this notation, A looks like raised to the C. That little c means complement. All right, that means not A. All right, so the complement of event A is everything that's outside of A. This symbol right here is called the intersection symbol, and it means and. Okay, the intersection. This symbol is called the union symbol, right, which means or. Event A happening or event B happening. And here's a general formula how to calculate or. Okay. And in a picture, here's how we figure it out. All right, if I want to figure out how much space this is, if this is event A and this is event B, you add up everybody that's in A, all right, and you add up everybody that's in B, but the problem is that middle part. All right, you've actually added this middle part twice. So if someone's in A or B, since we've added this middle part twice, and that middle part happens to be the intersection, since we've added it in there twice, we have to subtract one of them because we don't want to add it twice. We only want to add it once. Let's look at the next example. It says distance learning courses are rapidly gaining popularity among college students. Here's a probability model by age of the proportion of students taking at least one distance learning course. So people that take at least one distance learning course that are aged 18 to 23, they make up 57% of the students taking at least one distance learning course. People aged 24 to 29 make up that percentage or that proportion or that probability. All right, so on and so forth. So it says show that this is a legitimate probability model. So the only way this can be a legitimate probability model is if the sum of the probabilities equal 1. So we don't know if that's true or not. So what we have to do is we have to take the probability of 18 to 23-year-olds plus the probability of 24 to 29-year-olds plus the probability of 30 to 39-year-olds plus the probability of 40 and over. So 0.57 plus 0.17 plus 0.14 plus 0.12. All right, so if I add these things together, that looks like 74. If I add these together, that looks like 26. And when I add those, it does in fact equal 1. So it is a valid probability model. All right, number 2. It says find the probability that a student selected at random is not in the traditional college age group. So we want to find the probability that we're getting an 18 to 23-year-old complement. Okay, so complement means not. All right, so the easiest way to do that is just do 1 minus the probability of someone being in the 18 to 23-year-old group. So 1 minus 0.57. If you do that subtraction, you should get 0.43. There's another way you could have found it if I added these three numbers together, people that are not 18 to 39. 17 plus 14 is 31, plus 12 is 43. So 0.43. All right. And we'll do number 3 now. Find the probability that a student selected at random is 30 or older. So 30 or older is the event. Which outcomes correspond to that? Well, these people are 30 or older, but so are these. So what we have to do here is we have to add the probability of someone being 30 to 39 plus the probability of someone being 40 or older. So 0.14 plus 0.12, which is 26%. Okay, there's a 0.26 probability that someone taking at least one distance learning course is 26%. So moving on to the next section, two-way tables and probability. When we're trying to find probabilities involving two events, sometimes a two-way table can display the sample space in a way that makes probability calculations easier. The best way to approach these types of problems is to ask yourself what numbers should go in the numerator and which numbers should go in the denominator. And we're going to walk through the next problem here. All right. So this one says, students in a college stats class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether the student had a pierced ear for all 178 people in the class. Well, it's kind of nice when they give me the total number of people in the class, so that should be 178 there. All right. The two-way table shown on this page right here displays the data. Okay, so we know whenever we have a two-way table, the first thing we have to do is we have got to get our marginals. Okay, we got to get the totals of the columns and the totals of the rows. All right, so if I add these two together, 19 plus 84, that's 103. 71 plus 4 is 75. If I add those numbers together, it does in fact give me 178, so that's good news. All right. Now if I add down here, all right, well, before we do that, let's think about what these mean. That means in the class, there's 103 people with pierced ears. There's 75 people without pierced ears. All right, 19 plus 71 happens to be 90. 84 plus 8 happens to be 88. If I add those two numbers together, it does equal 178. So there's 90 males in the class, there's 88 females. Okay, so let's see how we do this real quick. So, suppose we choose a student, which means one student from the class at random. Find the probability that the student A has pierced ears. How would I write that? The probability that I have pierced ears. Well, how are we going to find that? Pierced ears would be yes. So we're going to find how many of those have it, 103, and how many total students are in the class. Well, there's 178. All right, so we can express the probabilities as a fraction, but we could also do it as a decimal. So if I do 103 divided by 178, okay, that is 0.5787 if I round. Or you can express it as a percent. 57.87% of the class has pierced ears. All right, this is an event. Having pierced ears is an event. All right. So, part B. How would we write this? Is male and has pierced ears. So the way we would write that, we want to find the probability that the student is male, and so we can use the and symbol, the intersection symbol, and pierced ears. So how are we going to find that data? Well, the person needs to be male, so we need to be looking down this column. They have to have pierced ears, so we have to be looking across this row. All right, so how many of the 178 people, how many are male and said yes? Well, 19. It's the intersection of that column and that row. So 19 would go in the numerator. Out of everybody in the class, that's 178. So the probability that I select a student at random that's male and has pierced ears would be 19 over 178, or as a decimal, 0.1067, or as a percent, 10.67. So, let's think about part C. You can do part C one of two ways. All right. So this probability is male, or, so that's the union symbol, has pierced ears. Okay. So there's an easy way and there's a hard way. I'm going to show you both, and you might like one more than the other. Well, we know the number that should be in the denominator. There's 178 people in the class. Okay, so that's relatively straightforward. Now, I'm just going to put a check mark in these four boxes if that describes having pierced ears or being male. So this person is male, okay? So that's male and yes. This is male and no, but it's still male, so it meets one of these two criteria. Male or means one or the other or both, okay? And this number in here, those people do have pierced ears. Well, even though they're not male, that's okay. They still have pierced ears. So it says or. All right, all you have to do here is add these numbers up. So add the 19 plus 71 plus 84. So if I do that, that's 174 out of 178. Which is going to be a really high percentage or decimal, 0.9775, or 97.75% of the class is male or has pierced ears. Now you could have done this a different way. To figure this out, you could have used the formula. You could have taken the probability of the person being male plus the probability of a person having pierced ears. But now you've double counted the intersection, so you have to subtract out male and pierced ears. So if you did it this way, well, how many males do we have? The probability of being male is 90 over 178. The probability of having pierced ears is 103 out of 178. But the problem is I've double counted these 19 people. Okay, I have double counted those. All right, so I have to subtract it. So 19 over 178. All right, so if you do that, this is the harder way in my opinion. 90 plus 103 is 193. 193 minus 19 is 174. So you'll get the same answer. You can use the formula, but it's a little easier to see in a two-way table. So other than a two-way table, sometimes it's nice to look at Venn diagrams because Venn diagrams can convey the same information. All right. When we draw a Venn diagram, we generally draw a circle for each event inside a rectangle, which is the sample space, and write in the raw number of individuals who are part of each event. If the circles are mutually exclusive, the circles should not overlap, since they have no outcomes in common. If the circles do overlap, then they have outcomes in common. So we have two events. We have A being a person is male, and event B is pierced ears. So that's how we're going to define these events. All right, so I'm going to draw a box. All right, and what I like to do in my Venn diagram at the bottom, I like to give the total. So there's 178 people we're looking at. All right, so this is event A, and this is event B. So let's think about what this is. The intersection here is people that are male and have pierced ears. So looking at the information in the two-way table, that would be male and yes. There's 19 people that would go inside the intersection. So I would write 19. All right. Now, what about this other part of A? That would be people that are males, but they don't have pierced ears because they're not part of circle B. So how many are male and said no? That's 71. All right. Now, what about over here? Event B is having pierced ears. So the 19 people are the males that had pierced ears, but we haven't thought about the females that have pierced ears. So how many females have pierced ears? 84. Okay. Now, what about should any number go outside here? Are there any people that are neither male nor have pierced ears? So that would mean female and no. So how many people are female and no? Well, 4 are. All right. So if you add up these 4 numbers, 71 plus 19 is 90, right? So between this number and this number, if you add them together, that would be 90. There's 90 people. Are there 90 people that are male? Yes, right there. All right. What about pierced ears? 19 plus 84 is 103. Are there 103 people with pierced ears? Yep. Okay. Outside, are there 4 people that said no to pierced ears and are not male? So not male would be over here, and no would be 4. All right. And does 90 plus 103 plus 4 subtract out the 19? Does that give you 178? And it would. Okay. So answering the same questions here, question A from above, they wanted to find the probability that someone has pierced ears. Well, looking just at the Venn diagram, you got the 178 down there. Pierced ears is event B, so we would add these two numbers. So 19 plus 84. So that's 103 out of 178. Probability of male and peer steers. All right, that's the intersection symbol and, so we're going to look where the circles intersect. So there's 19 there. So that's 19 out of 178. In part C, probability of male or peer steers. The total is 178. Okay. The people in here are male, so they fit one of these. The people in here are both, so they fit at least one of these. And the people in here have peer steers, so they fit one of these two criteria. So we just do 71 plus 19 plus 84. And when we do that, we get 174 out of 178. So there we go. That's how we answer the questions using a Venn diagram. All right, so let's look at the next one. Exercise. In an apartment complex, 40% of residents read USA Today. Only 25% read the New York Times. 5% of the residents read both papers. All right, so it says part A, make a two-way table that displays the sample space. All right. So up here on the top, we can say read USA Today. And either someone does or does not, so I could say yes or no. And over here, I can say read New York Times. And people can do one of two things, yes or no. So when we know when we look at everybody, it should add up to 100%. So I can put percentages in here, that's fine. So it says 40% of residents read USA Today. Only 25% read the New York Times. So in terms of reading USA Today, 40% do. So I can put 40% there. What do these two numbers have to add up to? Well, they have to add up to 100%. So 40% read USA Today, then I should know that 60% do not. All right. Tells me 25% read the New York Times. So this row needs to add up to 25%. Well, if 25% do read the New York Times, that means that 75% do not. So I can put that number in there. All right, now it gives me one more key piece of information. It says 5% read both papers. Well, if that's true, then 5% would say yes to both. And if I know that piece of information, I should be able to figure out these remaining three. Okay, 5 plus what gives me 25%? Well, 20% do. All right, 5% plus 4 plus what gives me 40? That would be 35. Okay, 20 plus what gives me 60? Well, that's 40. Okay, so there's a two-way table in terms of percents, but that's okay. It can be in raw counts or it can be in percents. So this means 5% of everybody reads both. 20% of everybody reads the New York Times but does not read USA Today. 35% reads USA Today but not the New York Times. And 40% of everybody reads neither. 40% reads neither. So we can make a Venn diagram to convey the same information. All right, so I'm going to let A equal read New York Times. I'm going to let B be read USA Today. We know that we have 100%, so I'm just going to treat this like 100. All right, so the numbers that go in here. The middle is the intersection. So how many read both? 5. So the number 5 would go in there. Okay. What is this part right here? That's the people that read the New York Times. So they would say yes to reading the New York Times. All right. But no to reading USA Today. So we would put the number 20 there. All right. What about this part of the Venn diagram? That's who read USA Today. So they say yes to USA Today, but they're not in the red circle. So it's no to the New York Times. So yes to USA Today, no to New York Times. That's 35. Okay. If I add these numbers up, these three, 35 plus 5 is 40, plus 20 is 60. How many are we still missing? Well, we're missing 40, and these are the 40 people that read neither, right there. They read neither. So the nice thing with the Venn diagram, you get your 4 numbers in here. Okay, 3 of them are inside the circles, and 1 of them's outside, because it's neither. All right, now let's do the 2 problems here. Part C. Find the probability that the person reads at least 1. That means 1 or both. So this is the probability that someone reads the New York Times or USA Today. Okay, so you can do this using the formula, or you can just think about it. Well, there's 20 people that just read the Times. There's 5 people that read both. There's 35 people that read USA Today out of your 100. So that would be 60 out of 100, or 60%. Part D says find the probability that it's neither. Okay, so find the probability. What does that mean? Well, to be neither means that it's the opposite of an or statement. So it's the probability of New York Times or USA Today complement. Because if they don't do either one, all right, either means or, all right, neither means not or. Okay? So either is synonymous with or, neither means not or. So you do an or statement, but you make it a not, you make it a complement. So here, all you would have to do is 1 minus what we just found. 1 minus 60 out of 100, which would be 40 out of 100. Okay. Or 0.40 or 40%. Or you could just look in here. There's 40 people that do neither. Or you can do here, no, no. There's 40% that do neither. And that is going to do it for section 5.2. So we'll stop the video there. Hopefully it all made sense to you.